All right. If you do have that bonus, if you attempted the bonus and you think you got it, I'll take it here. Well, I don't have many being turned in, so it's the fewer turned in, the more it's worth.
Completely wrong. Only 5 minutes I'd be done, but I need to finish doing it.
Okay. Well, turn it in.
Partial?
Turn it in. Let me see what everyone turns in. I'll base it on what people turn in.
Was there a wicked integral on there if you would have done it by hand? Was it like a pretty wicked?
No, not really. I mean, it was trig substitution.
Like I did the trig sub, and then I had to do integration by parts again. When I went
Should have been trig sub. Should have probably taken you to a power reduce, like a cosine squared or something like that, and then you could do that, and then. But you just have to get everything back in terms of your variable. So.
I went and mine like turned it to like integrate by parts again, and then I had to do another integral. So it was crazy. Yeah. That's why I
You had a what?
stopped and I just kept watching it. Yeah.
Theta over a number. Well, then you have to solve for theta then. You have to take arc sine or something like that to get theta. Yeah. Yeah. I don't know.
That's what I did. Yeah. But yeah. Well, no, that's how.
But then you have to integrate that square root. That might have been hard. Because that would have been trig sub anyway. All right, well, last call. Last call. Last call. Bonus, last call. All right.
I dropped some oil in mine.
Oil?
Yeah.
Okay. All right, I'm ready to get started. Is everyone ready? Oh, the exams. You should know your grade, right? I posted the grades. I explained that I only graded 6 of the 7 problems. So that was just after seeing what the average was starting to look like. I did that. So when I do hand these back to you, you'll have 2 grades. It'll be like a lower grade and then a slash and then the higher grade. Of course, the higher grade's your grade. The other one is what it would have been had I graded it, every problem. Just so you know, that's what that is. I'm going to hand these back later. Sorry. I need your attention right now. I don't want y'all fumbling through that. All right, we are going to start Chapter 8, series.
Is this the hardest part about Cal 2?
I don't want to say that right now. 8.1, sequences. Yeah, I don't want to say that this is the hardest part of Cal 2. The thing is, it used to be skipped a lot when it was taught here by a lot of instructors, and it's not something you can skip. So it's important. It's not necessarily harder or easier. It's just different. All right, so we're going to start out. The whole idea is to get to the idea of a series. And then from that, we can do some stuff. But to build up to series, we have to first understand what a sequence is. So I'm going to give you first the basic definition of a sequence, and then we'll get into some examples and look at some of the properties. Sequences, when you think sequence, you think of, what does it make you think of? Ordered pair? Like if I have a sequence of cars, it's just like, it's like a list, right? And it's exactly what a sequence is going to be for us. It's a list. And it could be a list of anything. In our case, it's a list of numbers. But the more precise definition is that a sequence is a function that goes, watch the way I write this, f colon double struck n arrow into script r. That's what a sequence is. It's a function f that what the heck does this mean? Well, what it means is that you have a domain. Remember with functions you have domains? That's the things you're allowed to plug into the function, right? Most of the functions we've dealt with in this class, the domain is the real numbers. You just plug numbers in, it spits out numbers, right? But for a sequence, your domain is not any number. It has to be this double struck n, which are the natural numbers. The natural numbers are the integers 1, 2, 3, 4, 5, 6, 7, 8, all of them, starting at 1 and going on. That's your natural numbers. Then they get sent through the function to something, and that can be anything. It can be a number. Okay, so the input of a sequence is a natural number. The output is a real number. So if you want to look at it, easily, it's everything you've done in your whole life, but you're restricted to only plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9 forever. Can't plug in pi. Can't plug in 1/2. Can't plug in -2. Got it? Now, let's take a look at what this looks like, all right? So what I'm going to do right now is I'm going to compare, as an example, I'm going to compare the function that we've all seen in our life, x squared, versus the sequence x squared. But we don't use x as our variable when we have sequences. That way you can distinguish them from functions. We usually use n squared. And we don't write f of something, we just write whatever the function is. So, that okay for now? And the way I'm going to do this is visually first. Would you all agree this right here is the parabola x squared, right? And what I can do is I can drag and I can make the parabola by plugging in values of x, right? So if I plug in like x is -5.5, I square it, I get 30.25. And if you put all those together, you get your graph, right? A sequence only allows me to plug in 1, then 2, then 3, then 4, right? So it'll be on the right side. My sequence will be on the right side. And it'll only be those points instead of the curved graph. So if I kind of take that other thing out of there, a sequence is just this list of points as opposed to a continuous graph. See it? Questions? Therefore, everything we did in calculus doesn't really apply. Because think about, like if I asked you to find the slope of the tangent line, Cal 1, on the parabola, can you find the slope of a tangent line for a parabola? Sure, right? Derivative of x squared is 2x, right? However, with the sequence, you don't even have a curve. You just have a bunch of dots everywhere. So you can't talk about a derivative because for a derivative, you have to have some sort of idea of tangent line. And it's just not going to work. Do you see what I'm saying? So it's very different than what we've been doing. Okay. Now, is it buzzing? Is it gone? I couldn't hear it. Usually I hear it. So the difference here is that the x squared looks like this, right? But n squared looks just like the dots, only on the right side. And you can't plug in 0. Pardon me? Well, kind of. Piecewise, the piecewise functions that we've had in the past, you usually had something between them. Like it wasn't just dots. Well, I'm looking for something. No. All right, is that all right? Okay, now we need a way of writing a sequence out. Like for the function, we always wrote like f of x equals and then the function. The way that we write a sequence, I wouldn't put just n squared. Here's how I'd write it. For the sequence n squared, I'd write a sub n equals n squared. So kind of look at the a as kind of like being the f, and then the subscript n is kind of like the x, and then equals this side is like the x squared. Do y'all see that? So the a is the name of the sequence, so f is the name of the function f, and then x is what you plug in, well n is what you plug in, and then what does it spit out? Here you square what you plug in, here you square what you plug in. Does that make sense? It's just completely different. You don't have the same exact notation. That all right? There's nothing fancy here. There's no trickery. Okay, we just get an idea of what these sequences do. So here's an example of a sequence. I'm going to make up a new one. Yeah. I would like for us to list this sequence. Let's go ahead and write out what this sequence spits out. So one way to do it would be this. Write down what you get when you plug in 1. So what would a sub 1 be? 2 times 1, which is 2. What would a sub 2 be? 2 times 2 is 4. A sub 3 would be 6, right? Again, nothing fancy here. So we could list them out, a sub 1, a sub 2, a sub 3, or we could write it out in a list in a set of braces. And that's the way we normally do. So I would write out, instead of this, okay, I'm not going to scrap it, but I'm going to say instead of doing that, we write out the list that starts at 2, then goes 4, then goes 6, then goes 8, and then keeps going. So when we want to say it keeps going, we say dot, 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 usually 3 dots. So that's the pattern, 2, 4, 6, 8, 10, 12. So would you all agree that's the even numbers? Yes? So 2n creates the even numbers. Can you come up with the list or find for me a sub n that gives you this list? So is that the same list pretty much? With the exception, I also want what in there? 0. So how can you get it? N minus 2? 2n minus 2. Isn't it just this list up here? Every single one of those minus 2? So it's, take 2 away from that, 2 away from that, 2 away from that, 2 away from that, and you create that. So this one would be a sub n equals 2n minus 2. List it out, you create the evens. So now I can create a list of even numbers starting at 2. I can create an even number list of even numbers starting at 0, right? Can you find the sequence for this? Two n minus 6, right? So again, all we're doing is kind of translating that one master list 2n, just moving it over, subtracting a number from it so we can move further down the list. Any questions? That's all right? Okay. How about this one? Can you create this list for me? 2n minus 1. Because it's every even number, right? Take 1 away makes it odd. So 1 is 2, but take away 1. 3 is 4, but take away 1. So that's just your even list minus 1. This is an important one, odds. Okay, right? That creates your odds starting at 1. 2n creates your evens starting at 2n creates your evens starting at 2. If you wanted to start it at 0, you would go 2n minus 2. Okay, so we know right now it appears that we can create all odds and all evens if we wanted to. Couldn't we? How about this? Here's another important type of list to create. I want you to create the sequence that will give you a -1, then a 1, then a -1, then a 1, then a -1, then a 1. Well, let's think about it. So sometimes when they're a little challenging, we want to kind of look at what each one is. This is a sub 1. This one's a sub 2. This one's a sub 3. This one's a sub 4. This one's a sub 5, right? So when I plug in 1, right? When I plug in 1, when my input is 1, it should spit out a -1. When my input is a 2, it should spit out. Oh. It should plug in. Plug in a 2, it should spit out +1. And then I plug in a 3, it should spit out negative. So every time I plug in an odd number, it should spit out a -1. Every time I plug in an even number, it should spit out +1. -1 to the n. Remember the property of -1 when you raise it to a power. If I take -1 and I raise it to the nth power, anytime n is odd, right, I get -1. Anytime n is even, I get 1. So does that work? Yes? Do you all agree with that? It is only natural numbers. See, look, what would a sub 1 be here? Anybody else who has that quiz? It's now or never. Not quiz, the bonus, sorry. -1, if I plug in 1, that's -1. If I plug in 2, -1 squared is 1. Thank you. Got it. I don't know if this addresses the whatever, if there was any confusion on this. This okay? Does everyone see that? Okay.
What I was thinking is, you said sequences because that's an exponential function, right? And you said sequences.
Good question. Good. The -1 to the end is not an exponential function because we no longer have what we would consider functions anymore in the sense of nice continuous functions defined on real numbers. And with exponential functions, you had restriction that with an exponential function, a to the x, a could not be a negative number, a could not be 0, and a could not be 1. But with sequences, you can have this -1 to the, and that's fine. So you don't have, it's not an exponential function, so to speak. Okay, what if I want to create this list? Oh yeah, this one up here, I forgot to name it, sorry. This is what we would call an alternating sequence. Because it alternates signs, right? It starts negative, then positive, negative, then positive, negative, then positive. It's alternating. So can you come up with the formula for this then? How about 8, -10, 12, -14, 16, -18, ... So whenever I look at sequences, I always try and look at the sign first. Okay, this is alternating, right? But it's starting out positive, then negative, positive, then negative, positive, then negative. So what we'll do is we'll still use a -1, right? But instead of n, what should I use? See, because when I plug 1 in, I want it to actually be an even number, don't I? So it turns out positive. When I plug in 2, I want it to be an odd number. Do y'all see what I'm saying? When I plug 1 in up there, I want -1 to actually be to an even number. I can do n plus 1, can't I? If I do +1 here, then now when I plug in 1, I get 2. When I plug in 2, I get 3. And then 3, I get 4. You see what I'm saying? That will create alternating still, but it'll be positive first instead of negative first. Is that the only thing I could have used? Well, I still need to get the 8, 10, 12. This just took care of my alternating. That's all I'm focusing on right now. That'll get my sign to switch. But could I have used something other than n plus 1? Like what? N plus 3 would have worked. N plus 5 would have worked. Because no matter what I use, if I do n plus 1, of course, when I plug in the first one, I get it even. If I do n plus 3, when I plug in 1, I get 4. If I do n plus 5, I plug in 1, I get 6. You see what I'm saying? And then it'll keep alternating. I hope that makes sense. Okay, that's my sign. Now I'm going to multiply that by, I need now to pick up the numbers. I need even numbers, starting where? At 8. 2n plus 6. So 2n creates my evens, right? But then adding 6 moves me over in that list. So instead of starting at 2, I'm going to start at 8. And then the next one would be 10, 12, 14, 16. Now I can check it just by plugging in here. A sub 1 would be -1 to the 1 plus 1 times 2 times 1 plus 6, which is -1 squared times, let's see, 2, 6, 8, which gives me -1 squared is 1, so 8. So that gives me my 8, which should be the first one. And then I could do the second one and show that that's going to be -10 and keep going, right? So we're kind of like looking at a list and trying to reverse engineer like where it came from, right? Ready for another? So like I said before, the first thing you want to focus on is the signs. If they're all the same sign, you don't have to worry about it. But if they alternate, you're going to have to work with a -1 to a power. So in this case, it starts negative, which means that I know that I can use -1 to the n. I don't need to do n plus 1. N plus 1 would start me positive, right? N starts me at negative. Okay, that takes care of the sign. Now what? 2, 4, 8, 16, 32 are not, they're all even numbers, but we're missing some, right? We have 2, 4, we don't have 6, we don't have 10, 12, 14. Good. It's 2 raised to the n. Those are all powers of n, or powers of 2, aren't they? The first number here, right, is 2 to the first power. The second number here is 2 squared. The next number here, 8, is 2 cubed. So 2 to the n gives us that. Yay or nay? Okay, so let's just step back real quick. Here's what we know so far. We can create lists of even numbers starting wherever we want in a list. We can create odd numbers starting anywhere we want. So for the evens, we use 2n. For the odds, we use 2n minus 1 or something like that. We can create alternating ones starting positive or negative. And it looks like we can create lists of powers of numbers also. And that's what we've done so far. Next example. How about -1. Well, hold on. Let me do it this way. -1, 1/3 through hold on, I'm making this one in my head. Hold on. You know what? Let's go. I need to alternate this. Sorry. This one's tricky. That's 5/27. They do alternate. Okay, so let's take care of that part of it first. Okay, they do alternate, and they start negative, right? So -1 to the n? Okay, so far that's what we know. Anything else you notice? Yeah? Multiples of 3, where? Oh, in the denominator. Okay, so
we can put like 3 to the power of n minus, yeah.
let's do this. Whenever you have a fraction, it's not obvious what's happening. Try and look at the numerator and denominator separately and see if you find a pattern in each of the numerator and denominators. It looks to me, maybe, and to some of you, that like 81, 27 are both powers of 3, aren't they? This is 3 cubed. This is 3 to the 4th, right? Now, that kind of breaks down after, as I keep going, right? The next one, I'm going to put it in red because the bottom 3 squared should be 9. It's not 9, it's 3, right? See what I'm saying? So I'm kind of like, that doesn't look right. But this one is 3 to the 1st power, right? And then the other one, 3 to the 0. What's 3 to the 0? 1. So actually, I could do that in blue. Yes? Do you have a potential answer? Okay, hold tight, hold tight. If you have it, good. I want to walk through this first one, okay? There's multiple ways to represent a sequence. There does not always have to be one answer. You can have multiple versions of the same thing that create the same sequence. Anything you notice in the numerator? 5, 7, those are odd numbers, right? But it would be great if we had what here? Like, you have 5, you have 7. It'd be nice if we have a 3 there, but we don't really have a 3 there, do we? Do y'all see it, though? If it was a 3 on top, what was I supposed to have on the bottom? 3 squared, and one of those cancel, and it's the 1/3. And then the next one should be a 1 on top, right? Which I do have. And on the bottom I have a 3. And then this last one should be, careful, -1. Right? Do I have -1? Okay, let's try and put this together. we have on the bottom potentially looks like what? 3 to the n, but we don't want to start, when we plug in 1, right? We don't want 3 to the 1 for the first one. We want 3 to the 0. So subtract 1 from it. And now when you plug in 1, you'd get 0 for that first one. On the top, it looks like the what? The odds starting where, though? At -1. So how are you going to do that? -3. I think we're going to have a problem. Yes. We're going to just do this because this, I've tried to make it in my head too quickly. Do this first one right here. This, see that negative sign right there? Just take it out. Because we're going to have 2 negatives there. So it'll cancel, so it'll be positive. Just take that one out. Let's see if this formula works. Look, this is going to do what? Alternate our signs starting with negative first, which we don't have. Bear with me. This is going to start the odd numbers starting at what? -1. And this is going to create powers of 3 starting at 3 to the 0. Now let's see if we can create that list from that. So let's see, what do we get when we do a sub 1? -1 to the 1 times 2 times 1 minus 3, which will be -1 over 3 to the 1 minus 1, which is 0. So we have -1 times, what on top? -1 over 3 to the 0, which is 1, which gives us 1. Do you see why I had to change that negative out front? Okay. So I get the first term of the sequence. So I'm happy about that. Let's see if I get the second one. A sub 2 is -1 to the 2 times 2 times 2 minus 3 over 3 to the 2 minus 1, which gives me, what's -1 squared? 1, right? Times 1 over 3. So that's 1/3. Is that what we have? So far it looks okay. Let me go one more. -1 to the 3rd. And then 2 times 3 minus 3 over 3 to the 3 minus 1. -1 cubed is -1. Times, what do we get up top there? 6 minus 2. So 3 over 3 squared, which is 9. That's -1/3. Is that our third term? Yes. And then from there on, we should be good. Does that make sense? Okay. That was a tricky one. Especially when I messed it up in the beginning with the minus sign out there. All right. Let's look at a couple others. How about this? I would like to define one for you. So let's list it out. What's that? Okay, we need to talk about this to make sure everyone knows what this is. All right? This is what we call n factorial. Comes up in statistics a lot, if you've taken stats. All n factorial is another way of writing a certain type of multiplication. So let me show you an example underneath it, and then we can generalize it. As an example, if I write 5 factorial, that means 5 times 4 times 3 times 2 times 1, but you don't necessarily need to write the 1, okay? 3 factorial would be 3 times 2 times 1. Okay? 1 factorial would be 1. And this is the big one. 0 factorial is equal to 1 by definition. What I mean by that is we define, in our mathematical system, we define 0 factorial to be 1. At this point, don't try and make sense out of it. Just, you'll have to take this one on faith for now, all right? So 0 factorial is 1. Whenever you have factorials, you have a restriction. N must be greater than 0, and n must be an integer. That means that you cannot do this. If you take 1/2 factorial, it's not defined. And this is really actually an important thing to know because, look, I showed you earlier x squared, right? X squared was this nice parabola, but when we defined the sequence n squared, it was only those dots, right? Well, n factorial is a sequence that there is no function that you could correspond it to. Does that make sense? No? Okay. With the parabola x squared, my sequence n squared were just the dots on that parabola, right? So I could just say, oh, look at x squared and look at the dots on it. With factorial, I could show you what factorial is by plugging in 1. 1 factorial is 1. 0 factorial is 0. 2 factorial is 2. 3 factorial is 6. And then I could keep drawing the dots, right? To get the dots for factorial. But there's no function, f of x, that you could put next to it that's a continuous function. Because factorial is not defined on all the spaces between the integers. So I can't connect it to anything we've studied before. Does that make sense? Factorial is only defined on integers. Okay, so let's list out these terms of this sequence. That, what I just stated right there, is going to turn out to bite us in the ass a little bit later because anything that we can connect to a function, we'll be able to do some calculus on. But things that we cannot connect to a function, like factorials, we're going to have to find another way when we're trying to figure out what these sequences do. What are the terms? So what's a sub 1? Sine pi over 1. What's sine of pi? 0. Okay, what's a sub 2? Sine of 2 pi over 2, which is 0. What's a sub 3? Sine of 3 pi over, what's 3 factorial? 6. 0. Sine of 4 pi over what's 4 factorial? 20, I don't know why I put 6. That's still 0. So the sequence is 0, 0, 0, 0, 0. But do you see the way the factorial behaves? You see that all you're doing is evaluating sine at different places. In this case, it's always 0. So your sequence written out would look like this. 0, 0, 0, dot, dot, dot. It's a sequence of zeros. You never know. I really just wanted to demonstrate how factorial behaves. All right. How about this one? A sub n equals n squared over n factorial. Let's list out the terms of this. So what would a sub 1 be? Or the first term here? 1 over 1, which is 1. What would a sub 2 be? So 2 squared is 4 over 2 factorial, which is 2 times 1, so that's just 2, isn't it? A sub 3 would be 9 over 3 times 2 times 1, so 9 over 6, which is 3 halves, right? A sub 4 would be 16 over 4 times 3 times 2 times 1, so 16 over 24. That reduces. What's funny is everything y'all were saying is what I was doing in my head as y'all were doing it. It was like 4 over 6 and then 2/3. All right. All right. And I can keep going, right? So let's list out the terms. 1, then 2, then 3 halves, then 2/3, ... Now, if someone gave you this list, 1, 2, 3 halves, 2/3, ... it would be extremely difficult to recover that sequence from that, wouldn't it? It would be very hard. I wouldn't do that to you, but this gives you an appreciation for when someone defines the sequence for you, you've got everything you need, don't you? But if someone only gives you a list of a few terms, you may or may not be able to go back from it. Do I make sense or not? Okay, now I think we're ready to start to move into the calculus of what's going to happen here. Because all this has been about is just defining a sequence, showing how we can, if someone gives us the sequence, we can list out the terms. If someone lists out the terms, we can try and recover the sequence, right? The main thing today is if someone gives us a sequence, where is it headed? So like, look at this sequence right here. Where's that headed? Starts at 1, then it goes 2, so it gets bigger, then comes down a little bit, 3 halves, and then 2/3, a little bit smaller. So what would happen as I keep going in this sequence? Where does it approach? That's the question. Someone gives you a sequence. What happens is you let the sequence go to infinity. Make sense? All right. So now we have, take one, pass it around, please. A lot of what I have, what I'm going to write down, I don't want you to have to write down, so here it is. We grab it. I'm tethered to my thing here. All right, you ready? Everyone have one? Okay, here we go. I'm going to mark up this page, but it's pretty much what you have here. First of all, we defined a sequence. And notice I put a set of braces around the a sub n up there. You can have those or not have those. Different books, different authors do it different ways. If you have a set of braces around the a sub n, it's understood. It's a sequence. If they're not there, it's okay also. All right? So it's a function, goes from natural numbers into R. So it takes in an integer starting at 1, and it spits out anything, pretty much. A sub n equals 1 over n would create that list, right? Now, the idea of the limit of a sequence. The limit of a sequence, right here, is basically asking the question, what happens is I let n go to infinity? As you go way out in the sequence forever, does it go somewhere? And this is like a limit that we did back in Cal 1. Limit as x goes to infinity is pretty much what we're doing. Now, if it does go to a number, L, then we say that the sequence converges. If it does not go to a number, we say it diverges. All right? Some other things. This is a big one for us right here, this theorem. And this is hopefully what I kind of already got across to you. It says that if you're trying to figure out what's going on with the sequence, right? You're trying to figure out what's going on with these dots. If those dots can be looked at as a function. So see I have a of x right here? Look at that as almost being like f of x. It's saying if there is a function that also draws that sequence, so it's like my x squared drew those dots in the very beginning. So if there's a corresponding graph that's defined on all real numbers, then wherever that graph goes, your sequence goes. Right? Does that make sense? Wherever x squared went, that parabola, if our sequence is just dots on that parabola, it's going to go where that parabola goes also. So if it's possible to just look at your sequence in terms of real numbers instead of just the integers, then wherever the function goes, wherever that function goes, your sequence must also go to the same place. Does that theorem make sense? Could you use that theorem for n factorial problems? No, because n factorial does not have anything that we could write in terms of all real numbers to correspond. Does that kind of? All right. We'll have to see when we get to some examples. So look at this example here. What we have is the sequence here. If I were to write the sequence here is a sub n equals n over n plus 1. So you could start writing out the terms of this sequence, right? What would the first term of this sequence be? 1 over 2, so 1/2. The next one would be 2/3, then 3/4, and then 4/5, and you keep doing that forever, right? The question is, what happens as you go to infinity? Well, that means take the limit of this as n goes to infinity. Before I can do that, though, I have to look at this n over n plus 1. Is there something in the real numbers, if you define that function over all real numbers, is that a well-defined function, something we've studied before? Exactly. X over x plus 1 is a rational function. Studied in college algebra. So there is something in the real numbers, a function defined on everything except -1, but that we can basically look at. So wherever that function goes, our sequence goes with it. And how do we find the limit of that? L'Hopital's rule. Because the numerator goes where? Infinity. Denominator goes where? Infinity. Infinity over infinity. Apply L'Hopital's rule one time. Derivative of top over derivative of bottom. Derivative of top is 1. Derivative of bottom is 1. 1 over 1 is 1. So that goes to 1, which means our sequence goes to 1. And then the picture below it shows it. The blue is the x over x plus 1 as a function. The red is our sequence. So you can see they go together, right? Squeeze theorem. The squeeze theorem says if you have 3 sequences, a sub n, b sub n, and c sub n. All right, so you have 3 sequences, 3 sets of dots. 3 sets of dots. If one of the sets of dots is always less than, let's say the first set of dots is less than the second set of dots is less than the third set of dots, then wherever those outside dots go, the one in the middle has to stay between them, right? Has to be squeezed between them. Right? If I always say, this one is below this one, and that's below that one, then that one has to be between the two. But if these two end sequences go to the same place, so as I go to infinity, the two outer sequences start to come to the same place, then what does the one in the middle have to do? Go to the same place. So it gets squeezed in between the two sequences. All right? That's the theorem. So if the two end sequences, that would be these two, if the two end ones, if those two, sorry, I got those backwards. If those two end ones both go to the same place, then the B sub n has to go there also. With me? Okay, here we go. Let's try this one. Now, I didn't leave any room on your paper to do this, so you might want to do it on separate paper or something. What is the limit as n goes to infinity of sine of n over n? So let me try this. Let me first ask you, can you look at this, bless you, as a function of x instead of n? In other words, is there something where you could create this sequence? Is there a curve that corresponds to it? Just like the previous problem. Yes, sine x over x, that's well defined. So we don't have factorials, we're not worried about it. Now, what happens? Take the limit as x goes to infinity. Where does the top go? Where does the bottom go? What's sine of infinity? It just keeps going back and forth, right? That doesn't exist. That limit does not exist. And the bottom goes to infinity. That doesn't matter. The top doesn't exist. So let me show you how we can apply the squeeze theorem. Right? Because right now, I can't even use L'Hopital's rule, can I? L'Hopital, because we don't have infinity over infinity, 0 over 0. So here's an application of the squeeze theorem. What I'm going to do is I'm going to write something down that I know for sure is always true. I see that I have a sine here, right? What's the one thing I know about sine? Sine of anything is always between what two things? Negative 1 and 1, right? Y'all agree? Stop doing that, man. Why do you keep doing that? That's just the property of sine, right? Always bounded between negative 1 and 1. Now, what I'm trying to look at here is what's happening to sine x divided by x, right? So what I'd like for you to do is come over here to your inequality on the right side and divide everything by x, both sides, like this. Oh, negative 1, thank you. I forgot the negative 1 there. Is that inequality still true?
Yes.
Would that inequality always still be true?
No, when x equals 0, wouldn't.
If x was 0, this wouldn't be right. And if x was negative, wouldn't the inequalities flip over? Why am I not concerned about that? That's right. At the end of the day, I'm really looking at only positive values. In fact, from 1 on, because that's where my sequence is defined. So not only will I never have 0, I'll never have negative numbers. So that division by x is okay. Now tell me about this right here and this right here. We could look at those as being two sequences. A sub n equals negative 1 over n. And this one over here, C sub n equals 1 over n. And in the middle, this one is my B sub n. Well, I'm saying B sub n, but there's an x in there. I'm really saying B sub n is my sine n over n. So these are all, this inequality is true, isn't it? I know it's kind of hard to read, but saying negative 1 over n is less than or equal to sine n over n, which is less than or equal to 1 over n. Y'all agree? Where do the two end sequences go to? Let n go to infinity. Dang it. Sorry. If I take negative 1 over n less than or equal to sine n over n less than or equal to 1 over n. And now I let n go to infinity. And here I let n go to infinity. Those both go where? 0. And therefore, if I let n go to infinity here, it must be squeezed between 0 and 0. And what's the only number between 0 and 0? 0. Pi. So that must go to 0 also. Now, what if the left side went to 0 and the right side went to 1? You haven't squeezed anything. All you've said is it's stuck between these two, but you haven't told me where it goes. So the idea behind Squeeze Theorem is to always try and squeeze what you're trying to figure out between two things that go to the same place. So the answer to this is what? 0. Now here's the graph that shows kind of the Squeeze Theorem happening. The green graph is 1 over n. The blue graph is negative 1 over n. And then sine n over n is the red one. So the sine n over n is kind of scattering back and forth, but it's always trapped between those two. So if those two start to head to 0, then the sine n over n must also go down there also. You see that? Squeezed in between. Next theorem. You should have this on your page, right? It says if the limit as n goes to infinity of the absolute value of your sequence goes to 0, then the sequence itself must go to 0. That's critical. If the absolute value of your sequence goes to 0, as n goes to infinity, then the sequence itself must go to 0. And I have two examples here. So let's take a look at this one. For this one, tell me what a sub n is here for this example. The negative 1 to the n times 1 over n. What's a sub n? Negative 1 to the n times 1 over n, right? It's the thing I'm taking the limit of? Yes? Now, what's the absolute value of that? What happens when I take the absolute value? What happens to this that negative 1 that keeps oscillating back and forth? It's just going to become a positive 1. So this just becomes 1 over n, doesn't it? Now, what is the limit as n goes to infinity of the absolute value of a sub n? Well, that's the limit as n goes to infinity of, what did we just say the absolute value of n was? 1 over n. And where does that go? 0. What this theorem says is, if you're having trouble trying to figure out what's happening to a sequence, look at its absolute value. If it goes to 0, then the original function, the original sequence also goes to 0. All right? So the answer to this question up here is that equals 0. Questions?
The reason why that negative 1 just go positive, so it's like it'd be like multiplying 1 times 1 over n. That's why
It's because if I take the absolute value right here, see this step right here? Forget this for a second. That's the absolute value of negative 1 to the n times 1 over n. But that's the same as the absolute value of negative 1 to the n times the absolute value of 1 over n. So I'm taking the absolute value of each piece. This piece in here is either going to be 1 or negative 1, right? Absolute value is 1.
Okay.
So it's gone.
So that's why, okay.
And so all you have is the 1 over n over there.
All right.
Okay, let's look at the next one. Oh, this one, I get so many students with this one. My goodness. What about this one?
So our a sub n is 1 minus 3 n, right? The absolute value is 1, so the limit is just
Okay, what's a sub n here?
And 1 minus negative 1 to the
Negative 1 to the n.
but the absolute value is just 1.
The absolute value of that is the absolute value of negative 1 to the n, which is just 1. And hold on, limit as n goes to infinity of the absolute value of n is then the limit as n goes to infinity of 1, right? Which is just 1. So the answer is 1? No. Can't be. Think about what this sequence is doing. What is that sequence doing? Plug in 1, what do you get? Negative 1. What's the next one? Plug in 2. Then 3. Then 4. So what it keeps doing is going back and forth. So why didn't this theorem work? Read it again. Hold on. Read what this says. If that limit goes to where? 0. Then the other one goes to 0. But if it goes somewhere else, they don't have to go together. So that theorem only works if that absolute value, after you do it and you take the limit, if that goes to 0, then you're guaranteed the original one went to 0 also. But if it goes somewhere other than 0, all bets are off. Okay? So what do we say then in this case? Well, you can tell by just looking at it, hopefully you can tell by just looking at it, that if you were to graph this, the first one we said was negative 1. And then if you go out to 2, you'd be at 1, and then negative 1, and then 1, and then negative 1, and then 1. So it keeps going back and forth like this. That's not headed anywhere, is it? So what we would say in this, not doesn't exist, we say diverges. Remember, we said that if it goes to a limit, we say converges, and we say to where it goes, and if it doesn't, we say diverges. Okay, you see that? Be extremely careful. I do not want to get you on a test on that, where you take that absolute value and then say, oh, it goes there. Nope. Is it indeterminate form? Not really, because negative 1 to the n doesn't have a graph that we could look at like x squared.
As n goes to infinity,
Mm-hmm.
wouldn't that have a positive 1? Because I remember in one of the videos you were saying that as 1 wants to stay there and infinity wants to make it really large.
That's right. But that means that indeterminate form is 1 to the infinity. That means that the base here was getting close to 1, and this was getting huge. Here, our base isn't getting close to anything. Our base is something. And then we can't, negative 1, see negative 1, you can't raise negative 1 to fraction powers. So this is kind of like n factorial. It's only defined on the positive integers. All right, where am I? All right, find notation. Oh yeah, here, this is just notation. Instead of writing out all this junk right here, limit, n goes to infinity, la 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 la, all we have to do is this, right? If it goes to L, then we write the sequence goes with an arrow to whatever the answer is. That's just notation. Let's try and find this next one. First question, can you do this with x's instead of n's and try maybe L'Hopital's rule or something like that? No, you can't do it. Can you tell me where the numerator and denominator both go, even though we can't use L'Hopital's rule? N factorial, as n gets bigger, that number gets huge, doesn't it? That becomes infinite. And then on the bottom, n to the n. That's n times n times n, n times. That's infinity also, right? But no L'Hopital, right? Do y'all understand why we can't do L'Hopital? What's the derivative of factorial? There is no derivative of factorial. Because you can't take a derivative as a single point, and that's all a factorial is just points. Not a nice curved graph. So we are kind of screwed at this point, right? Now, maybe there's something we can do with Squeeze Theorem, but maybe not. All right, this is where things start to get fun. So let's do this. Let's just write down what this means. All right, like if I write down the nth term, a sub n, that's n factorial over n to the n, right? That's what a sub n is. Now, by the definition, n factorial means n times 1 less than that, right? So we write n minus 1. So like if n was 5, it would be 5, and then times 4, which was 1 less than 5. And then the next one would be take 1 away again. So n minus 2, and then n minus 3. And I keep doing that until I get to where? You could go n minus n. I'm just going to go to 1, though. Okay? Does that make sense for n factorial? Are you sure? What is the bottom? What's n to the n? Isn't that n times n times n times n times dot 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 times n? Would you agree that there are the same number of factors in the bottom as there are on the top? In other words, I have n n's on the bottom, and then I have how many numbers on top? I have the n, and then the next one, next one, next one, next one, all the way to 1. So you could kind of line these up, couldn't you? Do you agree? Okay. Now, what can we say about this? Now we're going to come in with an inequality, okay? Watch. Do you agree that whatever that multiplies out to be, must be smaller than or equal to 1 times 1 times 1 times 1 dot 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 times 1 over n? So what in the hell did I do there? Maybe I can do it this way. Does everyone agree that 4 is less than or equal to 5? Yes? Because 5 is a bigger number? Okay, how about this? Does everyone agree that 1/3 is less than or equal to 2/3? Why? Because the numerator 2 is bigger than the numerator on the other side 1? Right? Agreed? So look at this fraction here. N divided by n is 1, right? So those are the same. But n minus 1 divided by n, tell me about that number. It's less than what? Forget the rest. What is n minus 1? Give me any number. I don't care what it is. Take 1 away from it and then divide by n. What can you tell me about that number? Smaller than 1, isn't it? Doesn't matter what it is. This could be 1,000 minus 1. That's 999 divided by 1,000. That number is smaller than 1, isn't it? So these numbers are the same, but this number is smaller than this number, right? So this inequality is looking okay so far? The numbers on the right are bigger than the numbers on the left. This number is also smaller than 1. That number is also smaller than 1, right? They're all smaller than 1 until I get to the very end. And isn't 1 over n the same as 1 over n? Now, I also know that's smaller than 1, but are you all okay with this? No questions? Sure. So you mean to tell me that we have this? That the n factorial over n to the n is smaller than or equal to 1 times 1 times 1 times 1 all the way until I get to 1 over n? Yes? But would you also agree that that's bigger than or equal to 0? Because n factorial over n to the n has got to be a positive number, right? What am I creating here? Squeeze theorem. See, the left side goes where? 0. Well, it is 0, so it stays at 0, right? But the right side, 1 over n, goes where? to 0 when I let n go to infinity. So if this side in the squeeze n going to infinity goes to 0, and this side in the squeeze goes to 0, then the one in the middle must go to 0. And therefore, the limit is 0. Which tells you this. N factorial grows really fast, right? Like if you type in, 50 factorial, that's a really big number. But if you do 50 to the 50, that's a huge number. And so as you go to infinity, what happens is the numerator is getting big, but the denominator is getting big so fast that it just squashes everything down to 0 as you go out. That's kind of tricky, huh? Get used to it. I mean, this is the way things are going to be in here, I guess. So trying to apply squeeze theorem, we couldn't do a limit, couldn't do L'Hopital, we were stuck, we had to do this. Catch up? It's big, it gets bigger faster than n factorial does. That's what I was just saying. If the ratio goes to 0, then that means the bottom got huge faster than the top did. Yep. That's, yes. Well, as you go out, it's faster, yes. Mm-hmm. It's greater, yes. Always, though? Yeah? Always. Yep, it's always. All righty. Well, there's not many things that grow faster than n to the n. I mean, you could do n to the n to the n. That would grow faster. But, the idea of something to itself, that grows, that's pretty quick. All right, let's continue. Let's take a look at a general situation where we have a sub n is r to the n. Here, r is a number, everyone, just so you know. I didn't put it here. R is a number. We have a couple of results, which I'm not going to go into. You could do it yourself, but you must know that these things are true. If you take a number to the n, and that number is between -1 and 1, okay, then that sequence goes to 0. You let n go to infinity, it goes to 0. If if r equals 1, then the sequence is just 1, 1, 1, 1, 1, 1, 1, and that just goes to 1. And if the absolute value of the r is bigger than 1, it diverges. It becomes huge. And then I have 3 examples right underneath it. So why does 1/2 to the n go to 0? Because 1/2 is between -1 and 1, right? So I'm using this first one right here. What about 2 to the n? Diverges. 2 is greater than, the absolute value is greater than 1, so it diverges. And then what if it's 1 itself? Well, 1, 1, 1, 1, 1, 1, that goes to 1. Okay? More definitions. A sequence a sub n is said to be increasing if a sub n is less than a sub n plus 1 for all n greater than or equal to 1. That is, increasing just means as you move from left to right, the dots are getting higher. The dot next, okay, if I draw a dot, the next one's got to be higher. Next one has to be higher. Next one has to be higher. That's increasing. Decreasing is the opposite. So it goes down. Linear function would be increasing this way if the slope is positive and decreasing this way. But notice on both of these graphs, the top one up there is increasing. But also notice that it is bounded. I remember a colleague of mine and I were talking about, it's one of the first things when I first started working here. one of my colleagues had come up to me and said, if you have a function whose derivative is always positive, that means the function is always going up, right? Then is it possible that, does that mean that it's unbounded? Does that mean that if the derivative is positive, it means it has to go up forever, right? Always? But does that mean that it can't have a ceiling to it? Does that make sense? But if you just take a function that does this and just has an asymptote right here, that function is always increasing, isn't it? But it has a cap at the top. So just because something is always going up does not mean that it goes up without bound. Now, of course, a line does, right? That's increasing, and it keeps going. There's no maximum to it. So you can have both cases. It doesn't have to be that it keeps going forever. Did I make sense with that or not? But never, but it could have a ceiling that it never passes. Because that's the property of the real numbers. You can always get closer to something without getting there. Just by going half the distance every time, right? Okay, but for us, sequences are the same thing. Increasing means as you move to the right, each dot gets higher. Decreasing means as you move to the right, each dot gets lower. Now the idea of a monotonic. Okay, if a sequence is increasing or decreasing, either way, then we call it a monotonic sequence. So monotonic is more general. If I say, hey, a sequence is monotonic, I'm not telling you if it's increasing or decreasing. I'm just telling you it's one or the other. Got it? And then finally, a sequence A sub n is said to be bounded above. Can we shut that door, please? Those air dryers are terrible, aren't they?
They drive so fast.
They do dry fast, but I just think about all like the microscopic stuff that gets blown around, and you know. I know I always close my eyes and like hold my breath. All right. So any sequence is said to be bounded above if there is a number m, capital M, such that the sequence is always less than or equal to m for all n. That means no matter what term of the sequence you're in, no matter what dot you're looking at, it's always below or equal to that number. It could be. It doesn't have to be. You could have more than one upper bound. Because if your asymptote is here, any line above that would also be an upper bound. Like look at that one over there, right? You would say that the x-axis or y equals 0. You would say 0 is an upper bound of that. But so is 1. Because the sequence is always below that also. Yes. And it would never touch. So that would be an example of an upper bound. See, later on, and for those people who are going to go study and do more math, there's the idea of an upper bound. Then there's what's called the least upper bound, which would be the lowest upper bound. In this case, in that case right there, the lowest upper bound would be 0. Yeah. The asymptote. Okay, but for us, an upper bound or bounded above just means there's something that it never gets bigger than, right? And then bounded below, we use a little m, and that means that there's a line below it that it never goes below. So the sequence is always above that, bigger than it. Make sense? In either case, whether or not it's bounded above or below, it's called a bounded sequence. And that all leads us to finally what's called the monotonic sequence theorem. It says, every bounded monotonic sequence converges. See, here's where we're getting, everyone. We're getting to a point where we're going to be looking at sequences that we can't do anything to. Like we can't do any L'Hopital, we can't do any algebra like I just did where I had all those ones. Squeeze theorem, we're having trouble with squeeze theorem. We can't find anything to squeeze it into, so we need something else. This theorem is something we can use. But you have to have the conditions satisfied. They are what? You must have a bounded sequence, which means there's either a roof, right? A ceiling or a floor to it. Okay, it's got to be bounded, and it's got to be what? Monotonic. Monotonic means increasing or decreasing. If it's bounded and monotonic, we can guarantee it converges. Why? Does that make sense? Come on, let's think about this. Like, let's use the brains that we're wanting here. Converge means it goes somewhere, right? Okay, so let me come up with something. Let's say I have a sequence here, and let me bound it, okay? Let me bound it. I'm going to put a capital M on it, all right? Now, let me also tell you that it's monotonic. Is there a way that I can draw this without it converging if it's monotonic? If it's increasing, look, there's no way, right? Because look, I can't come back down, and that has to be the ceiling, so I have to converge, right? Does that make sense? Yeah. What about the other way, though? What if this was decreasing? If it was decreasing, right? Decreasing, could you make it happen?
Only if you have a outer wall like that. If the M was down.
So it would have to be bounded below.
Yeah.
So if it's bounded above and increasing, it converges, right?
Yes.
Bounded below and decreasing, it converges. Does that make sense? Now, I put something in red here. It does not tell us what it converges to. And this is again, going to happen a lot with us in this course. We're going to be able to look at a sequence. I'm going to be able to tell you, look, it goes somewhere. But I'm not going to be able to tell you where it goes. But I'm going to be able to tell you it does converge. It's not like the limit. It's basically like saying there is a limit, but I don't know what it is. As opposed to saying there is no limit, which means it's not headed towards one place. Okay, continuity convergence theorem. If a sequence goes to L, okay, if the sequence goes to L and f is continuous at L, then the limit of the function equals the function's value at L. What in the world does that mean? So let me try and help you out with this one right here. All right, let's try and find this limit. Cosine pi n, what happens here? Cosine pi n over. Well, yes, can this be rewritten as a function of x? Well, cosine pi x over x plus 1 is well defined, right? I mean, that's a nice function. So I could be looking at this instead. Pi x over x plus 1. Now look at the theorem that I just had up here. This says if you have a sequence that goes to L and f is a continuous function at L, then if you plug that sequence into the function, your answer is whatever you get when you plug the limit into a function. So I think this can really confuse students. All it's saying is this. I am allowed to take the limit right here, inside there, figure out what this does. Figure out what that does, and then plug that answer into cosine. I can do that because cosine is a continuous function, isn't it? That's where that continuity comes into play right here. So look at this f out here as being your cosine. That's your cosine out here. And then what's inside is your sequence. Make sense? So what is that limit inside? We said infinity over infinity. So take the derivative one time, L'Hopital, top and bottom. So you just get pi, right? So this is going to be equal to cosine of pi. Cosine of pi is what? -1. So the answer is -1.
So like, it means that
Go ahead. What?
the AM approaches -1.
A sub n here approaches pi. For us here, a sub n was what was in here. That goes to pi. And then we plug it into...
Oh, so -1 is not out.
Mm-hmm. All right. Okay, before I get to these examples, I want to do one more thing. This whole idea of monotonic. I would like us to show that a sub n equals n times n squared plus 1 is monotonic. What does monotonic mean? It's either increasing or decreasing. Now, I think this is pretty easy to show if you just start plugging some numbers in. So let's do it. Let's plug in what's a sub 1, or you know what, let's just list out the sequence. Plug in 1 and what do you get? 1 over 2. Plug in 2, you get 2 over 5. Plug in 3, 3 over 10. Is it obvious that each one gets smaller? Right? But that is not a sufficient way to show something is monotonic. In this example, it's easy. But we need a better way for problems that are not as obvious as this. Because we might have sequences that they oscillate back and forth and do some weird stuff, and then eventually they start to go somewhere. So with this example, let me show you how you can show it's monotonic. All right? So right now, I want to show, WTS means want to show, that a sub n equals n over n squared plus 1 is monotonic. Now, just by looking at it, it looks like it's decreasing, right? So I want to show then that the a sub n, how is it related to the next one? Is it bigger or smaller than the next one? It should be greater than a sub n plus 1. Do you agree with that?
Yes.
So whatever I plug in, like if I plug in 2, that term should be bigger than what I get when I plug in 3, because they get smaller as I go, right? So I'd like to show that. Go with me? Okay, so what is a sub n? N over n squared plus 1, right? The question is that bigger than what I get when I plug in n plus 1, which would be n plus 1 over n plus 1 squared plus 1. That's a pretty important thing for you to see what I'm doing there. I'm comparing these two things. What I get when I plug in n versus what I get when I plug in n plus 1. Now what I'll do is multiply, like a cross multiplication, to clear fractions. So I multiply the left side by n plus 2, or n squared plus 1, multiply this n squared plus 1, and then I will also multiply both sides by the n plus 1 squared plus 1, n plus 1 squared plus 1. So what we get here is some canceling. On the left side, The n squared plus 1's cancel. On the right side, that cancels. Can you multiply the left side out? Go n through here and n through here. So I have n plus 1 squared plus n greater than n plus 1 times n squared plus 1. Questions? I'm going to go ahead and expand that out right there and then distribute an n through it. What did you get? N times so n cubed plus 2n squared plus n, but then I have a plus n. On this side, n cubed plus n squared plus n plus 1. I kind of switched the order. That's n cubed, that's n squared, and that's 1. Now we have some of the same things on both sides, don't we? So we can subtract and cancel. The n cubes cancel. The one n squared cancels. Let me see. One of these n's cancel. When I subtract that, and that'll become an n squared on the left. I still have a plus n, right? Greater than 1. I can factor out an n times n plus 1. Is that greater than 1? Question. Is that true or not? Why? Well, not any number. Remember what n was. N was what we were plugging in, right? And what did we always have to start with? 1. So look, if n is 1, the smallest n could ever be. 1 times 2 is 2. 2 is bigger than 1, right? After that, it's pretty much over, isn't it? I mean, you can... Does that make sense or not? We've gotten it down to something where we could just make the simple argument that that's always bigger than 1. You don't even really need to factor out the n. Okay, because what I did was I said, look, I think that this is monotonic, right? I need to show it was monotonic. Now, I didn't know if it was monotonic increasing or decreasing. I listed out a few terms. It looked like it was decreasing. And I said, okay, then what does it mean to be decreasing? Decreasing means this. I needed to show that that is true. So I set it up, and at the very end of that inequality, I got to something that is true, always. This is good. This right here is true for all n greater than or equal to 1. Now, of course, n integer. N being an integer. I mean, it holds even if n isn't an integer. It'll hold for 1.5 and 1.6. But for the value n equals 1 all the way out, that'll always be true, which means that that inequality was always true right here. That's always true, which means that it's monotonic decreasing. That make sense or not? Well, unfortunately, that's, I think, where we're going to have to stop. Yeah, well, you know what? I mean, we still have a lot to do. Well, there's 1, 2, 3. Y'all want to stay an hour late today? I'm just kidding. You want your test back.